Thank you very much. Well, this is the first time that I speak at a tech conference, so I'm a bit nervous. So please smile and act as if everything I say is very interesting. This will help me a lot. Well, good afternoon, everybody. My name is Juanjo Madrigal, and it's a pleasure for me to be here and share with you some knowledge about probabilistic streaming algorithms, which is a very broad and interesting topic. I won't go into much detail, just share some ideas and some intuitions and some examples. Well, as the name says, these algorithms have to do with probability and random processes. That is something that, well, it is widely used in programming, sometimes with really good results. And well, what's the problem that these algorithms want to treat? Well, these algorithms have to deal with the problem of querying over massive amounts of data. For instance, this is a real use case. Consider all the search queries that are made on Google for one day, and perhaps we want to know how many different queries are there, or which are the most frequent ones. Well, the issue is that these data sets are so big that one cannot rely on making room to store all the information somewhere in order to inspect it or compute something. Instead, one has to work with a stream. That is, your data comes element by element. You may write something about it, and then you let it go, never to see it again. I would like to get a bit more formal about all this. What we need is an algorithm that has some internal state, and that processes elements one by one, and that when the stream is over from this internal state, I want to answer some questions of my interest. If we want to have exact results, indeed, we don't have much, we have little freedom of choice. For instance, if we want to know the exact number of different elements, we have to keep a set with all the elements that have appeared so far. And if we want to know the frequencies, then we have to keep a map with all the frequencies. But there's a problem that, well, these algorithms are very simple, but they do not scale well. Sometimes these data sets are so big that it is not only that the data set itself doesn't fit anywhere. It is that the internal state of the algorithm, the set or the map, doesn't fit anywhere either. And it may be something huge, it may be something really difficult to work with. So, and it may be somewhat absurd too. For instance, imagine having a stream of elements in which the first 10,000 elements are all different, but they are followed by 1 million of elements that are all the same. From the very beginning, we'd be forced to drag an enormous data structure, an enormous set, an enormous map, and this would be very, very awkward. Perhaps we can do something lighter if we're open to approximate answers. And this is what we want to study here with some examples. And the first example is the Alon-Matthias-Szegedy algorithm, which was one of the first ones to be created. Well, when I work with a stream, one of the things that I may want to know about it is the frequency moment. Frequency moments are related to statistical moments, and they study the behavior of my stream. In this case, it consists in well, finding the frequencies of the element of the stream, and then raising them to a certain power, which is the order of the moment, and then sum everything. For instance, F0 is the number of distinct elements in my stream. OK, that's nice. F1 is the total number of elements in the stream, And then we say, well, F2, what does F2 measure? Well, this F2 measures how balanced are the groups within the stream. Because frequencies are squared, big frequencies lead to a very high value of F2, even at the cost of having some other smaller groups. So in this sense, uneven distributions, like the one here, will tend to have higher values of F2 more than smoother ones. Nice. But if we want an exact computation of this frequency moment, of this F2, then we would have to keep a map with all the frequencies, and we know that this may be too much memory. So instead, we would like, we would like to estimate it. And how can we do it? Well, these three guys, Alon, Matthias, and Stegeti, came with a very clever idea. They said, well, you will do the following. Take your stream and choose one element at random. For instance, this B here. And then you will count the number of times this element appears from the beginning up to the selected event, up to the selected item. In this case, 2, because there are 2 Bs. Then this number, which is M, you will create the expression to M minus 1, and then this value will be multiplied by the total number of elements in the stream. And then all this process will give you a number, and this number will be the estimation for F2. Now, this is something that, that is randomized. I mean, I could have chosen another element, and then there would be another outcome. But it is something that, in average, is equal to F2. Why? Well, because here we may see all these 2m minus 1's values for each possible selected element, and it is chosen in such a clever way that all these 2m minus 1 values for each element sum up to the square of the frequency. So when I sum everything, it is the exact F2. So the average of all the numbers have also to do with this F2. So that's nice. But well, there is a problem here. There are 2 problems indeed. This process, as I have explained it, it is not suitable for streaming. Why? Well, because for 2 reasons. First reason, I have said choose an element at random from the stream, but it is a stream. I mean, I don't know which data is to come. I don't know how many elements are left. So choosing an element at random, it is not so easy. And once the element has been chosen, then what should I do? Should I go backwards to inspect the previous elements? I mean, that's not possible because it is streaming. So as described here, I can't do this workflow in streaming. But perhaps we can make it work with, I don't know, some little changes, perhaps. We'll try. Well, the first improvement will be, OK, you will select one element, and then you will count your elements from the selected item onwards. Because it is logically equivalent, but it is better for streaming because I don't have to go backwards. Nice. But we still have the very big problem, which is how to choose an element at random from a stream when I do not know the data that is to come. But indeed, I can do it. How? And the key is to have a previously selected element, but for each new element, perhaps I switch to the new one. More concretely, I will switch to the nth element with probability 1 over n. Why this decreasing probability? Well, imagine that I say, no, it will be a fixed probability of 50%. That is, for each incoming element, I will always change to a new element half of the times. Then, even if my stream has 1 million elements, half of the times I will be selecting the last one. And that's not fair. That's not truly randomized. So now we see that with these two improvements, then this workflow is suitable for streaming. And then we have a very, very simple implementation of this algorithm from 1996. This is a very easy Python code. We have n is a global counter, and then selected is my selected item. Count is a local counter related to this selected item. And then for each element in my sequence, I may switch to a new one or remain with the previously selected one. So very easy indeed. Now, that is very cool, and this algorithm gives me an estimation that may be close or not to the real value. But in terms of memory usage, it is really good. If I want to use the exact algorithm, I would have to keep one key and one value in the map for each distinct element. And there may be thousands or millions of different elements in my stream. I really don't know. But with this AMS algorithm, I just have to keep one key and one value. So that's very nice. That's awesome. Except for a minor detail, or perhaps not so minor detail, that this algorithm has really bad accuracy. For instance, in our example, real F2 value was 50, and our approximation was 36. So really bad indeed. But well, there's a solution which is, well, you may just simulate several processes in the same pass. But look, not in several passes because I'm doing streaming. Just one pass, but simulating several independent random processes. And then I will take the average, and my accuracy will go up. Then in this case, well, now I have to keep in memory one key and one value for each simulation. It's more than before, but it is still far better than the exact algorithm. Perhaps imagine that I take the average of 100 simulations. With 100 simulations, my average may give a very good estimate indeed. Now, I have to keep 100 keys and 100 values, and that's much more than before. But it is still less than for the exact algorithm that I may have thousands or millions of different elements. The crucial point here is that with this algorithm, I have an upper bound of the memory needed. And with the exact algorithm, I don't have, there is no such upper bound. Nice? OK? Well, so now with having said all this, we may say, oh, OK, so which are the good properties that a streaming algorithm should have? Well, it should be able to process elements one by one. OK. It should also have little state or memory. And it should also have a reduced variance and small error. That is something that I can always improve by simulating the same process several times in the same pass. OK. Now, I may think, can we do something better? And the answer is yes, we can do many things better if we use hashing. Hashing, as many of you know, can also be understood as a probabilistic technique because hashes generate sequences that do look random. I mean, the values of the hashes of different elements are distributed, follow a random distribution. But there is a crucial difference, and it is that the hashes of equal elements are equal indeed. And that's very important. With hashes, we may devise a new algorithm and that perhaps has better behavior in many things. We will use a hash function that produces for each element a +1 or a -1. That's not very difficult indeed. One may take a standard hash function that generates ones and zeros, and then I may look at the first bit. And if it is 1, I keep the 1. If it is 0, I change to -1, whatever. So imagine that in this case, my hash function for A and C produces +1, and for B produces -1. So what will I do? I will compute the hashes of all the elements coming, and then I will sum everything. And when I have the total sum, at the end, I will square it, and this will be my estimation for F2. As before, if I choose another hash function, I would have another value. But in average, it's F2 again. Why? Well, intuitively, it has a lot of sense, because if I have many small groups, then some of them will be positive, some of them will be negative. They will cancel each other, and then the final sum won't be too high. But if there is a very frequent group, then it will always be +1, +1, +1, or -1, -1. And then what I get in the end, when I square it, it will be very, very high. And also, one may see from the formula of the square of the sums that well, the cross products disappear, and so on. And that's nice, because in this case, with this improved F2 algorithm, then I only have to keep one value for each simulation. Before, I had to keep one key and one value. So that's better. But indeed, well, there is an even better advantage of this algorithm, which is, well, what happens if I want to process my streaming with multiple machines? Is that even possible? Well, let's see. With this new algorithm, it is possible, because its machine will process a substream and then computes the total sum in the substream. And then before squaring it, I will sum everything. So if one thinks about it, well, it is logically equivalent to having worked with a single stream in the case that all the machines are using the same hash. That is very important. This is something that is not possible with the previous algorithm. I mean, there is no way in which the information for each substream may be combined for something that is logically equivalent to working with a single stream. Okay, so now for the properties that I want for a good algorithm, I will also ask that it is easily parallelizable. Okay, and with all these wishes, well, now we're ready to move on to one of the most popular and implemented algorithms, which is the HyperLogLog. For the HyperLogLog, the goal is, as we said before, to know how many different elements are there in a stream. If we want to have exact results, then we have to keep a set with all the different keys. If we want something better, we'll use hashing, and then for each element, we'll generate a long enough sequence of ones and zeros. Then what we will do is really simple indeed. For each incoming element, we will compute its hash, and then we will look at the number of leading zeros in this hash. And we will keep track of the maximum number of leading zeros that we have seen so far. Just that. Very simple indeed. imagine that someone says, OK, I have seen all the elements in my stream. I have computed all the hashes, and I have seen a hash with 5 leading zeros. And I say, OK, nice, that's great. But imagine that this person says, OK, I have seen a hash that starts with 27 zeros. And then I say, oh, OK, that means that the hash is 0, 0, 0, 0, 0, many more zeros. So, well, that's quite impressive. I mean, 27 leading zeros, what could have happened? Well, perhaps this person was very lucky or very unlucky, and he saw 27 leading zeros in the hash of the first element. It's possible, but perhaps it's more reasonable to think that this person has seen many elements in the stream and computed many hashes and and then for some has seen 27 zeros. But well, this person must have seen many different elements indeed, because if I have 1 million elements in my stream, but they're all the same, then I only have one hash, and it would be really strange that it starts with 27 zeros. So it seems that this number of leading zeros has to do with the number of different elements in the stream. If someone sees a hash starting with 3 zeros, then it is reasonable to think that perhaps this person has seen all the other 3-digit combinations, which are 8 in total. There is no strict guarantee, but more or less it should be close. It makes sense. So for a maximum of m leading zeros, we should infer that more or less there are 2 to the m different elements in the stream. But this more or less is not very precise. So then mathematicians come, they like precision and they like accuracy and formalism and so on, and they say, well, it's 2 to the m multiplied by a certain correction factor. Even more, if we want to improve accuracy, we may reserve some bits at the beginning of the hash, and then create some buckets for all the combinations for these reserved bits. And then the number of leading zeros will go to the corresponding bucket. So this will help reduce noise and variance, because perhaps in the first element I have had very bad luck and it had lots of leading zeros. But well, it goes to one bucket and the other buckets are still OK, are still realistic. So that's nice. And then in the end, I will combine all the results with a special mean, which is called harmonic mean. It is different from the arithmetic mean, and then multiplied by some correction factor. It happens that this harmonic mean and this correction factor have really complex formulas, and the papers in which these formulas are deduced have even more complex formulas. And this is something that mathematicians really love and programmers really hate. But anyway, if we want to use it rather than design it, we may just believe it. And we don't have to compute all these integrals on the fly. We may just compute them once and tabulate them. OK, so and now I may ask, well, how many bits should I reserve so that my HyperLogLog is accurate enough? And before answering this question, I have to do another question, which is, well, what do you mean by accurate enough? Because in probabilistic algorithms, one cannot hope that the result is always accurate, because it is probabilistic, and then they may fail. So instead, we play with 2 parameters. We say we want our estimations to be very accurate most of the times, and then we play with these 2 parameters. And when we fix an epsilon and a delta that are OK for our quality standards, then there is some formula that says the number of bits that I have to reserve in order to get this accuracy that I want. So, this HyperLogLog easily fulfills all the first 3 requirements. And with parallelization, something really curious happens here. And it is that, well, when we're working with different substreams, the way in which the information should be combined is not really obvious. For instance, here imagine that I have the exact number of different elements that I have in each substream. Even with this information, I can't do anything with it. Because, for instance, here we have 3 different elements in each substream. With the first and the second substreams, I still have 3 different elements. But with the second and the third substream, I have 6 different elements. So it is not enough to know the number of different elements in the substream. We would need to have the entire data structure, the entire set with all the elements, and compute the union, and we know that this is too heavy. However, with the HyperLogLog, this structure can be easily combined, because when I have different elements, it is more likely to have seen more leading zeros. So when I have the maximum number of leading zeros in each substream, I may just take the maximum of all, and this is logically equivalent to having worked with just one stream. And if I have different buckets, then I may combine them bucket by bucket, taking the maximum. So indeed, this HyperLogLog may be parallelized, and this makes this algorithm really good for counting the number of different elements in a stream. So that's nice. And for the most frequent ones, we have this another very popular algorithm, which is the Count-Min Sketch. And as we said, the goal of this new algorithm is to find the most frequent elements. As before, if we want to have exact results, we would have to work with a map, which is something that may be very heavy for many different elements in the stream. Instead, we will use hashing again, but this time our hash functions will have a pretty different aspect. Indeed, we will be working with with many independent hashes. Each of these independent hashes will give us a number out of a target range. This is not very difficult to do. I mean, I may have a single hash function, and then I may I may divide it in some pieces, wherever. There are many implementations of independent hashes. And well, then for each element, I will apply all these hash functions. So for each element, I will have a list of numbers out of this number range. And then what should I do? Well, we will create a table with one row for each hash function and one column for each number in the target range. So when I have a new element coming from the stream, I will compute all the hash functions. For instance, for element B, which is the first one in my stream, H0 gives a 7, H1 gives a 4, H2 gives a 9, and so on. So then for each row, I will take the selected number, and for each of the cells, I will update them 1 unit, considering that all cells start at 0 by default. When a new element comes, perhaps it is a different one, and then there are different hashes. So different cells will be updated, not the same as before. OK. But it may be, for instance, for next element D, it may be that there are some collisions. It may happen, especially if the table is very small. OK, now we go on with the next element, which is a C, with the hash values and the cells to be updated. Then the next one is another A. Next one, another B, another C, another D. Then we have a different element, which is an E, and there are many more collisions. And now, well, stop, wait. What are we doing? Are we doing anything that is helping us to keep the frequencies? For instance, we would like to know how many Ds have you seen? And then I may think, well, for each D that has come, I have computed the hashes, and then I have updated these cells. Then there cannot be more than 2 Ds, because each time that a D has come, I have updated this cell. So no more than 2 Ds have appeared. There are cells with bigger numbers, but this is due to collisions. I will take the minimum of all the cells to give my answer, to give my estimation of the frequency of D. Is it possible that all cells have had collisions? Well, it is possible, especially for a small table. Our estimation may be greater than the actual value of the frequency. But if the table is big enough, our estimation will be quite accurate. But how much accurate? Well, if I fix some epsilon and delta that I want, then doing some math, I may get the dimensions of the table that I have to use. If epsilon and delta are small, you see that the W and the D grow bigger. So that's very nice. Our algorithm has all the properties that we want, and the tables may be combined if the algorithm is parallelized. So that's really good indeed. We have a very good algorithm, isn't it? Well, no. I mean, because there is a very, very big problem. And the problem is that, well, we wanted to have a ranking with the most frequent elements, and we don't have a ranking. We have something that is very useful, that for a given element estimates the frequency of this element. But in order to have a ranking, then I would have to scan all the elements again and find all the frequencies and then create my ranking. And this would be terrible, but indeed it is not possible because it is streaming and all the data has gone. So what can we do? Well, we will enrich our table with some additional structure. Imagine that we want to know the n most frequent elements, I don't know, 100. Then the core of the algorithm will be in our table as before, but we will also have a temporary top n ranking. Then for each new element in the stream, I will update my table, just like before. But I may also update my ranking. How? Well, if the element is already in the ranking, then I will update the frequency 1 unit. OK, that's nice. If my element is not in the ranking, but the ranking is not full with n elements, I will initialize it at the very end with frequency 1. Nice. The tight spot is when the new element is not in my ranking, but my ranking is full with n elements. The element is not in the ranking, but it has appeared, so perhaps it should overtake the last elements in the ranking. But I don't have any clue about the frequency of this element. So I will estimate it with the table, and then, if needed, I may enter the pair in my ranking. But since the table has made an estimation, the ranking becomes estimated as well. OK? Now, if we would like to see some very simple example, well, I will take Don Quixote de la Mancha, which is a very famous Spanish novel. It's not a very big corpus for this purpose, but it's fun anyway. OK. So I will look at the text and then work with the different words. For instance, for HyperLogLog with 10 reserved bits, the estimation is quite good. I mean, this algorithm really shines with very, very big cardinalities, the order of 10 to the 9, while this corpus is 10 to the 5. But indeed, we see that it is quite a good estimation for an algorithm that just counts zeros. I mean, it is quite striking. And in order to get the most frequent ones, for instance, the top 50, well, we see that the Count-Min Sketch with this ranking also gives really good results. You may see that the words in the beginning of the ranking have exact frequencies. This is because they have been words that have entered the ranking very early, never been out, so they haven't been messed with an approximation, with an estimation of the frequency. At the bottom of the ranking, we see that there is more divergence, both in positions and in frequencies. But we see that, in general, these are very good results. And, well, that's everything. I hope that you have enjoyed this talk, so thank you very much for being here.